Hi, this is a short video on a very important number for calculus called e, and its special role that it plays for exponential and logarithmic functions. Now this number e is transcendental, a lot like pi. It's an irrational number that goes on and on forever with no pattern in its decimal places, and there's the first few digits of it. Now, we use it extensively as the base of both exponential functions and logarithms. So we often talk about e to the x, that nice exponential function, or log base e to the x, which we have a short form for. It's the ln of x, the ln of x. It's the natural logarithmic function. So if you ever see ln of x, you'll notice there's no base written there, and it's implied to be e. Now, there is absolutely nothing special about these logarithmic or exponential functions. They behave in exactly the manner you would expect for bases that are bigger than 1. So if we were to, say, draw y equals e to the x, all we'd be drawing would be an exponential function with a base bigger than 1. Likewise, if we were to draw y equals ln of x, we'd be just drawing a logarithmic function with a base bigger than 1. So y equals e to the x would look something like that. Exponential growth, whereas y equals ln of x would look something like that. And of course, we could have our little line of reflection, y equals x, since those two functions are inverses of each other. Now, if we talk about domain, range, the y-intercept, x-intercept, horizontal asymptote, vertical asymptote for the two different functions. We'll notice all the symmetry we should normally see for a function and its inverse. So the domain of y equals e to the x is the same as it is for all our prototype exponential functions. And that means that the range of y equals ln of x has to be the same. And you can see that there on the graph. The range of y equals e to the x, of course, we only get positive outputs there. And that's exactly the domain of our logarithmic function of ln. Now for the y-intercept, we have the point 0, 1. And for the x-intercept of the ln function, we have 1, 0. The x-intercept of the exponential graph, we have none. Same thing for the y-intercept of the logarithmic function. All the roles of x and y are being swapped here. The horizontal asymptote of y equals e to the x is y equals 0. The vertical asymptote of y equals ln x is x equals 0. And we've got no vertical asymptote for y equals e to the x, and no vertical asymptote for y equals ln of x. All the symmetry we would expect. And of course, all the properties of exponential functions and logarithmic functions apply to e to the x and ln of x. So for instance, all the log laws and exponent laws still hold. So I could simplify this, for instance, if I want to use an exponent law as the ln of e to the, I add the exponents since they have the same base. Those powers have the same base. I get this. And then I ask myself, okay, the ln of something, that's the exponent you raise e to get that something. Well, we can see exactly what you need to raise e to get this power. It's 3x plus 4. Those two functions are inverses of each other. So our ln function will go and exactly extract the exponent of that power. So nothing to worry about. It's just a very special base that you're going to talk a lot about in your calculus class. But don't worry, it behaves just like it should for an exponential or logarithmic function.